It's all clear? You still have a question? No? Okay. Okay, so let's talk about particle surface area and porosity. So I'll quickly go through some of the characterization aspects. So we'll not spend a lot of time, but hopefully I will finish you. Yes, I know I'm standing between you and your lunch, right? So I will not take much time. So, okay. Okay. So why surface area is important? For most of the processes, for any food materials that we deal with every day, it could be dissolution, it could be heat and mass transfer, burning rates, catalysis, filtration, fluidization, etc. Most of these properties, downstream properties, are influenced by, by surface area, right? So surface area affects, again, I didn't include here, coating process, mixing process, powder to powder mixing, etc., will be influenced by, the surface area of particles, powders. Okay, we'll go through some of those characteristics. Again, specific surface area, how do we calculate? It's again the surface area over volume, right? So R mass, it could be either meter square per gram or square per meter cube. It could be either based on mass or volume. So from that you can see smaller particles will have a larger surface area, right? If you take 1 gram of small particle and 1 gram of large particle, then small particle will have a larger surface area, right? That's a specific surface area. So coarse particles, like for example, if you're talking about glass sphere, it will be about centimeter square per gram, okay? But if if it's an average particle like sand, then it will be about 100 centimeters square or 1 meter square per gram. Very fine, their surface area will be very high, because if it's porous, then the exposed surface area will be high, right? Right. So, one example here, I've given is activated carbon, right? Activated carbon mostly we use for water treatment, etc., right? So there, you need a larger surface area so that it can get them, absorb the minerals and pass through, pass the water through the pore space, okay? So again, activated carbon usually has a large surface area, but we can use surface area to understand how the products are manufactured too. Again, I'm not talking about products here. This is an example of study. What they did was they collected sand particles from different areas, okay? Beach sand, other types of sand particles. You can see from France, Israel, USA, etc. And then they calculated or determined the surface area just to see how those sand particles are formed. Okay, so the production process, again, we can relate that to food powders. So the production process will affect the surface area of the particle. Okay, one just again quick example here, you can see this number 11, that's from Canary Islands, which has a large surface area than the other sand particles, because these sand were formed by volcanic grains, volcano activity that led to that formation of sand. So that again, volcanoes that resulted in larger specific surface area of particles than other process like sedimentation, etc. Okay. So again, the understanding here is we can understand the manufacturing process or production process based on the specific surface area. Okay. So if you wanted to modify specific surface area, then you will have to change the production process. Okay. So common two methods, again, you would have learned about these, right? Chemical sorption or chemisorption and physisorption, those are common two methods used for again finding the surface area of the particle, right? Again, you either coat with chemicals or use some gases that adsorb to the surface of the particle, and from the, I believe we will go through in detail in a minute, okay? From the amount of gas or chemical adsorbed on the surface, you characterize or quantify the surface area, specific surface area, right? Again, chemisorption is commonly used, but sometimes make sure when you are using chemicals to quantify the specific surface area, make sure it doesn't react with the solids that you're using. Okay. You all would have learned about BET theory, right? Okay, that's the common thing that we use. Okay. So most common, we assume that it's a mono layer formation of the particle, right? So if you're using, for example, gas, if you wanted to calculate the specific surface area, we assume that when you pass, we send gas through the solid, it forms and a mono layer adsorbed on layers on within those particle surface, and from the amount of gas adsorbed on the surface, you characterize the surface area, right? So very easy measurement and simple measurement. So typically we use nitrogen, but again, if it's still very small surface area, krypton gas is very common. These are again non-reactive gas that gets adsorbed on the surface. Okay. Anyone have used gas adsorption? No. Anyone have used moisture absorption? Probably you might be using later on, right? But anyone have used moisture absorption instrument? No. Water activity? No, not water activity, but no one have used moisture absorption instrument. No. Okay. So it's again the principles are very similar. Okay. You all would have learned about different types of isotherms, right? So based on the adsorption on the surface, the relative pressure or the pressure at which the gas is sent inside and the volume adsorbed will change. Okay. Again, very common in very common in most of the solids. You will see type 3, type 4, and type 5. Type 6 is most common in when you have layer wise adsorption. If it's more than monolayer, it goes by stepwise. Okay. Can anyone guess what will be the adsorption isotherm for a food powder? What type? Any guess? Which type of adsorption isotherm you will see in food powders? Food powders. Type 2? Any other guess? Type 5. Okay. But you said gave the right answer first. Okay. So more very common is, you'll see type 2, maybe sometime type 4. Why, type 2 again common is first, it's absorbs a lot on the surface. Okay, then it, there might be some absorption, so it kinds of plateaus, and then again, once there is uniform cover of liquid over the layer or gas over the layer of solids, it starts forming multi-layer adsorption. That's why you'll see, sudden increase again, or at high, high relative pressure. So it's very, same theory for moisture absorption and these, gas adsorption. Okay. So again, volume of gas adsorbed, you can use gravimetric or volumetric method. Most time we use, volumetric method, right? And again, if you use moisture absorption instrument, any time during your PhD or masters, you will see that, you use this volumetric method. Okay. Again, some products will have hysteresis. Do you know why there will be hysteresis? Hysteresis, again, it's a difference between adsorption and desorption isotherm. Okay. So why there will be a hysteresis, or why there is a difference between adsorption and desorption isotherm? Any thoughts?
So because of the damage of capillary pores during the.
Oh, it's too heavy on science. Okay. Yeah, maybe it might not damage the capillary force, but when it starts absorbing, so some for example, I'm talking about moisture absorption, right? So the moisture might get chemically bound to the particle. Okay, so when you bring back the cycle desorption, the chemically bound water will not come out. Same for gas adsorption too. If it chemically bonds to the solid, then you might see a hysteresis, difference between sorption and desorption pattern. Okay, so that's what happens.
Sir, in type 5, it is mentioned in x-axis that relative volume. Is it
Yeah, it's, you can use either volumetric or measure, but the example, it's from the book, so he might have took this example from a relative volume measurement than a relative pressure. So you can use both pressure and very same principle. You would have measured true density of solids, right? We'll talk about density more. It's the same principle that we use, pressure difference and get the amount of gas and get the porosity or pore space. So again, common theory that we use, the BET, the Brunner, Emmett, and Teller theory, again assumes a monolayer adsorption of the gas on the solid surface. Okay, and again, here's the theoretical equation, and again, most commonly used for most of the solids, including food powders, pharmaceutical solids, and most of the solids, you use this equation. Again, it's using the relative pressure, change in pressure, and I will walk through how we do this calculation, okay, and then get the surface area of the particle, okay. Any guess how do we use this equation before we go into that calculation to get the surface area? Can anyone explain how can we use this equation to get the surface area? So again, V is the volume of gas adsorbed and Vm is the volume of gas that forms a monolayer. Okay. So you know the size of the gas molecule, right? So if you know the size of the gas molecule and if you know the volume of the gas that's used to form a monolayer, then you can get the area, right? So that's the simple principle that we use. Again, getting the relative pressure and then again using this equation. So it's a plot this as a linear equation. Okay, you have an intercept, you have the relative pressure that's known. Okay, you know the relative pressure, so plot this. Okay, and you know the volume of gas that's absorbed, and then you know the intercept and you know the constant, right? So using that, you calculate this. Again, from the intercept we we calculate the constant C. Then I'll go through some of those calculations again. Just quickly again, if the constant is more than 100, again single point BET at isotherm is also common. If you don't want to wait for long, if you wanted a quick measurement, so single point BET is also common. That means you can see here you ignore the intercept, so direct relationship between the volume adsorbed and the relative pressure. Okay. So again, once we know the Vm, that's a volume of gas needed to form a monolayer. Okay, so you can calculate again using you're using gas, right? So you'll know the Avogadro's number, the projected area of the single gas molecule. Okay, and then the molar volume of the gas. Those are known for most gases. So you calculate again the surface area. Okay, so again as the picture indicates, you can see just assume one monolayer formation of gas on the surface of the particle. Okay. In simple calculation, this again simple calculation for if you're using nitrogen as the gas. Okay, so again mostly for single point measurement you can just use them. Okay, not sure how many of you will be measuring, but just keep in it's a simple way of measuring. Major assumption we make here is single monolayer adsorption of gas molecules on the surface of the solids, right? So if high surface area, then nitrogen is commonly used. As I said, krypton is so krypton is also common for low surface areas. But again, depending on the surface area, it might take long hours. Like if the surface area is smaller, then your measurement might be quick. But if it's very porous particle like activated carbon, it might take a lot of time. Okay. So the other common method, permeometry. Okay, so how much fluid flows through that solids or powders. Okay, how permeable it is. Using the permeability, you can calculate the surface area. Okay, And again, I'm sure you would have learned all these equations that we talk about in your undergrad, but you might have forgotten. Okay, again, calculates the surface area based on again how much pore space or void space is using this permeability relationship. So one common relationship is a Kalman and Kozny relationship. You would have learned about this, right, during undergrad, some fluid mechanics class, maybe. So again, based on the assumption, from the pressure difference and how much pressure it takes to pass the fluid through the bed of powders, you calculate the, surface area of the particle. Again, one of the major assumption here is all the void space or pore space is connected. It's like straight line. Okay, might not work all the time, but for simple calculation purposes, it gives good characterization. Okay. Again, that's the relationship that we use to calculate from pressure difference, and then using other fluid parameters, you can calculate the surface area. I'll skip through those calculations again. And again, from the pressure difference, usually it comes to all those particle characteristics that we talked about. If cross sectional area, if you know the surface area of individual particle, and then you calculate the overall specific surface area. Okay. Skip through this. Again, for spherical particles relationship. So the another one relationship ergon, you would have learned about these two again, little more in-depth measurement. So in Kalman-Kozny relationship, so you assume that the flow is laminar. Okay, so it's constant flow through the bed of solids. But ergon relationship, it gives an additional term for turbulent flow of the fluid through the bed of powders too. Because most often, the flow is not laminar, right? The flow will be some turbulent flow inside too. So it gives an approximation for turbulent portion and the laminar flow of the solids through the powders. Okay. I'll skip through those calculations. Again, there are instruments that we can use to use those Kalman-Kozny or ergon relationship to calculate the surface areas. So one common is constant head permeameter. Again, we keep the sample, send pressurized liquid through the sample, and based on the pressure difference, again use all those good looking equations to calculate the specific surface area. Okay, this is a simple measurement and easy to use. You might have used these flow manometers and bed manometers too, mostly for finding the pressure difference. So again, same thing, same principle. You keep the sample in and send the fluid through the solids to get the specific surface area or porosity. Okay. Again, as said, Kalman-Kozny can be used, but it doesn't give the turbulent flow through the solid. So ergon might be ergon relationship might give a better quantification of your specific surface area than a Kalman-Kozny relationship. Okay. Okay, I just quickly went through it. Okay, but if you have any questions, let me know. Any questions? If you're using Malvern master sizer, it usually calculates the specific surface area too. Okay, additional to particle size, it can calculate this specific surface area too. Okay. Particle porosity. Let's talk quickly again. Go through the particle porosity. So porosity again, we're not talking about the bulk porosity. Okay, it's individual particle porosity. Okay, so again, if it's highly porous, it increases the amount of void space that will increase the specific surface area, right? So when you are increasing the surface area, then there could be higher mass transfer or dissolution, chemical reactions. There could be more other downstream processes that are influenced by this particle porosity. Okay, one common, application in at least in food industry is the agglomeration of powders. So when you agglomerate powders, for example, milk powder or coffee powder, you add some liquid binders. Okay, so this amount of porosity or the specific surface area will influence how much binder that you need to add to make a good agglomerate. As I said in the previous lecture, you don't want to add lots of binders. It should be optimum, right? You cannot waste money too. So it can help with finding the appropriate binder liquid. Okay, so just comparatively, a non-porous, comparing non-porous solid and a porous solid, usually you can that it will have a high specific surface area, right? If it's porous, more surface is exposed, then high specific surface area and also pore volume. In general, we don't characterize in depth of the particle porosity. Okay, but when you take any single particle, you might see different types of pore spaces. Okay, there could be open pores, closed pores, dead end pores, etc. And based on the sizes, also you can characterize the particle porosity. Okay, so why does the pore size matter? How does it matter? Because for example, again going back to agglomeration, or so the liquid binder particle size should be optimum, so that it's not getting caught in micropores and it's not available for liquid bridging or bridging between the particles. So the particles should be high enough that they remain on the surface and is available for forming agglomerates. Okay, and again we can characterize these two, but it takes a lot of time and effort to characterize these interconnected pores or small pores within one single particle. Okay. So as I just said, highly influences wet granulation or any kind of granulation process. It affects the amount of binder that we can add. Again, the binder, when you add some binder, it should be available to form agglomerates. If it's getting absorbed into pore space, then your binder is not useful, right? You'll have to add more and more binder to get these agglomerates. So highly influences agglomeration. Again, porosity and tensile strength. So highly porous materials may form and again depending on the product may form a better compact, because when you compact those pore spaces breaks and then there will be higher surface to surface contact. Okay, that can lead to again a higher tensile strength depending on the type of solid. So for agglomerated products too, again I am giving an example from pharmaceutical solid, but it's common for food powders too. How the agglomerates is formed will also affect the dissolution behavior. For example, if you have again not going in detail into the graph, but if the solid materials or individual kernels or individual particles are spread across within the granule, then their dissolution behavior will be better than if it's just agglomerated in one location. Okay, so these are the individual particles in a large granule. Okay, so depending on how you form a granule or how you agglomerate, that will affect its downstream performance. Okay, it's for example the dissolution behavior. And same thing for porosity. So again, how the pore space or void space are within the granule. Okay, so if all the pore space is concentrated in one location, then their strength and their compact properties will be highly different than if the pore void space is spread across. Okay, so you can see mostly the fracture strength again will be higher for again the same sample which has all the void spaces again concentrated in one location. Okay, but if it's spread across, it might affect the strength, it might reduce the strength. Okay, but you can see it's almost same porosity. Okay, so again when you go and work for an industry, these things will affect a lot. How you form the agglomerates, how you are agglomerating the powders, how you are adding binders, etc. Okay. Mercury porosimetry used to be a common method to get those individual particle, pore spaces, but with lots of hazards, involved with using mercury, it's no longer, highly used, no longer used in, characterizing particles, but gives good, estimation from a small to large range of, particle size. Okay. So again, very similar to gas adsorption theory, it's very simple measurement. You pump mercury through it. So amount based on the volume of mercury that's adsorbed by the particle, you calculate the individual pore space. Okay. But more and more common nowadays is using X-ray microtomography. Okay. So again, X-ray microtomography, and if the resolution is high enough, it can capture almost all the void space and pore space within the granule and particles. Okay. It's like any X-rays. Okay. So it usually scans into 2D images and stitches them into a 3-dimensional granular particle shape. Okay. From that you can characterize all internal voids, internal porosity, etc., etc. Okay. It's very easy to use, but it takes a lot of time, and it's not an not a cheap machine. It's very expensive machine to buy, to X-ray microtomography. The advantage also, we can differentiate the different particles. X-ray, right? It works based on the principle of density, right? So if you have different density particles within the granule, you can easily identify where and how the granules or particles are mixed when you are forming an agglomerate or a large granule. Okay. I'll show an example here again. You can segment individual particles from the binder that you are adding. So again, you'll have to do, the machine doesn't do, but this kind of post-processing. So once you get the X-ray images, you post-process and segment them based on the difference in density. Okay. So again, gas adsorption, permeometry, highly used in pore space. Talked about it, affects a lot of downstream processing and other process, but one of the common method that we use is X-ray microtomography, to get the individual pore space within the solids. Okay. Any questions? I think that's the last slide. There are some standards that you can go through and some references. Okay. Okay, it's time for questions now. I quickly went through. I know I didn't know how much time I will take, but if you have any questions, we'll come back to some of these, at least the X-ray microtomography, when you talk about powder density too. Okay, questions? Yeah, go ahead. I know you have a question.
How this surface area porosity affects the stability of a product?
That's a good question. So, stability, excuse me, stability in what? In liquid or stability as such?
For any product, mostly for powder product.
So, stability again, if it's highly porous, when you are handling, it might break off. But if it's very with less porosity, your attrition might be little low. Okay. When it comes to dissolution, you want less stability, right? So you want them to dissolve quickly, right? Then you need high pore space, high porosity. Okay.
For liquids,
Hmm?
liquid,
Yeah, in liquids. What is?
like the stability effect of these properties on stability.
Oh, in liquid, like suspensions. Okay. In suspensions, yeah, you may want low porosity so that the liquid is not being absorbed inside the void space, right? If you have less void space, less pore space, there might be again depends on the type of solid or particle. It might have better stability. That's why most of the emulsions or the particles that are used in suspensions will come with a coating. What other questions?
So in terms of cost, like if we have to increase the pore size or decrease the pore size for binders,
For what?
pore size.
Yeah.
Like in the particle, we have to increase the pore size or decrease the pore size to reduce the cost of the binder.
So in general, you want less pore space. When when you want to use less binder. Yes, if it's high in pore space, again, binder can get absorbed inside, right? Inside the particle itself, then they will not be available for forming liquid bridging between the particles, to form agglomerate. So lower pore,
Agglomeration is done after dissolution or like
no, before, same like, if you are making,
like in instant soup.
yeah, instant soup. So usually, they mix different powders and agglomerate into, it's not large agglomerate, but small, powders, right? So when they agglomerate, again, you want, maybe less porous, material so that you are.
Sir, why we agglomerate it?
Oh, there are lots of advantages. Yeah. So easy shipping, handling, and you get more product uniformity. Because if you are just mixing into powder form, you can still segregate, right? But if you are agglomerating, then you still have all the ingredients inside that one granule. Okay, so that's a major advantage. It's common in all food, pharma industry, and it's easy to handle too. So very fine powders like 50 micron, 100 micron powders, it will be very difficult to make them flow. They will not flow, their flow behavior will be challenging and poor. So they agglomerate it, so they better flow uniformly. When you are going into a process machine or something, you wanted them to flow uniformly. So they agglomerate it and then make them flow. What other questions? Are you all thinking, or are you all waiting for me to say, okay, you can go? What's that? Go ahead, tell. Jokes are to be shared. No questions? Okay, so have lunch. I think we'll meet again at 2:30, right? So I think you will be free from me this afternoon. You have a lab, I think, this afternoon, and using some equipment. But I will see you tomorrow. We'll talk about more about densities. Densities.